Hello, this is the 9th review session for CS333. The topic of this review session is operator overloading. Now, throughout the semester we've used a number of operators. We've used the stream insertion operator. That's the operator we use every time we write a cout statement. That's what some people refer to as the less than when they read it back. We've been using stream extraction. That's the two greater than symbols every time you use cin or an input file. We've also used a number of other operators, less than for comparing strings, integers, and doubles, logical equivalence, the double equal sign, not equals, and a number of other ones. Now that's just a small subset of operators. I can define typecast operators, bitwise operators, for example, the negation operator, any number of operators. But tonight, this review session, I'm going to focus on three main operators. The stream insertion operator for output, less than for comparing two items, checking to see if the item on the left is less than the one on the right, and logical equivalence double equal sign. The double equal sign. Logical equivalence are two things equal. And this will be built on our running room update example. Now what I have open right now is the original room update example, not the original, but the most recent version from the ADT's discussion. Now when we last left with this example, we had reached a point where we had an array of rooms, we had a print all room summaries function, and we had reorganized our room into a proper class with private data members and all of the get and set functions. That's where we left off. Now, if you'd like a more detailed discussion of the final ADT version of the code I have it right now, go back to the last 15 or so minutes of review session 8, the previous review session on ADTs. But just to refresh your memory, the basic premise was I wanted to update a series of rooms. I started by prompting the user, how many rooms would you like to update? Then I prompt the user for each of those rooms. The cost per square foot of the flooring, the width of the room, and then the length of the room. And then I create that room and I add it to my array. Then print all room summaries. And this is a function that just takes all of the rooms and prints them one at a time. And at this point, it uses the display function. Now note there is one small change since the most recent review session. There is one small change. I have modified the display function to take a single argument. So the display function takes an output stream. Now an output stream can be an output file stream or cout or cerr, anything that guy can use for output. And I've modified display to pass it in. So instead of hard coding cout, I can use any output stream. And yes, I have left that as cout.precision. That is a type, and that is one you'll see in the remaining example code. But it doesn't affect the discussion. But the point is my display function is now generalized. I can now use it to output to the screen, to cout, to output to the screen, to see error, to output to a file, or for those of you who have worked with it, to output to an output stream. But that's just a small change. All I've really changed is the fact that now I can use this display function for any output stream instead of just cout. But let's go ahead and run this and refresh our memories real quick. So let's example 1. So let's say we have 3 rooms. Let's say this first one is a utility closet. Let's say it's 4 by 3 feet. The second room, let's say this is a hallway in an entry area. Let's say I'm doing slightly nicer flooring. Let's say it's 8 feet long and 4 feet wide. Then let's say I'm doing a dining room, for example. So let's do a little bit nicer for the flooring. And let's say it's 14 by 20. And then I get the output summaries for each of those rooms. What I entered, the unit cost, the area, and the total cost for that room. Now what I'd like to do is reorganize this code. So well, not necessarily reorganize, but enhance my room so that I can write cout my room variable instead of having to use this display function. What I would like to be able to do is back in update room here is instead of saying collection I.display, I would like to be able to say cout collection I and have that work. And we can do that, and we'll see that how that works in the next example. So example 2. Let's look at our main interrupt. So this is update room in example 2. Now I've decided this example, you know what? Logically, if I'm updating my house, if I'm replacing flooring and I have a limited budget, I'm not going to do all the rooms at once. And in the general case, we can make the assumption that if I am on a limited budget, I will do the cheaper room first. Meaning I will replace the flooring in the room that will cost me the least money, and then I'll move on to the next least expensive, the next least expensive, and so on. And that's where the sort rooms function comes into play, and I'll revisit that in a moment. But the only difference here is now I'm going to enter all the rooms, and then sort all the rooms, and then print them. So we'll come back to that in a moment. But as we go through this code, update room, once again the main function, we'll see that the main function itself hasn't changed, with the exception that now I have this call to the sort rooms function that will place the rooms in my sorted order. Now if I scroll down to sort rooms, we'll see that I am indeed sorting them. Now I'm using the worst possible sorting algorithm, and you'll see my commentary there on that. The worst possible sorting algorithm that can ever be used, bubble sort. Bubble sort is the worst sorting algorithm. It exists purely for academia. Never use bubble sort, period. Bubble sort is a worse sorting algorithm than Internet Explorer is a web browser. Once again, you can tell I don't like Internet Explorer too much. But the point is, do not use bubble sort. Now, I'm sorting the rooms. Now, I want to sort the rooms based on cost of flooring. Meaning, if I have a room, if I have 3 rooms, which one will cost the least? And I want to place them in order of least most expensive, second least most expensive, and so on and so forth. So now I look here. I am going to compare 2 rooms. A room, let's say room number J and room number I. And I'm going to compare the flooring cost of both rooms. Now I know that whenever I compare rooms, I am going to be comparing flooring costs. That is the constraint based on this program. I know without a shadow of a doubt, if I'm working with my room data structure, when I compare 2 rooms and I want to place them in an order, it's going to be based on the total cost of flooring. So ideally what I would like to do is instead of writing collection J dot flooring cost and collection I dot flooring cost, I would like to write something more along the lines of this. Collection J less than collection I. Now at this point, I haven't written that operator. We'll come back to that in the next example, but keep that in your mind. How can I simplify this program by defining that operator? The less than or comes before operator. And we'll see that in the next example. If I'm comparing 2 rooms, a room J and a room I, and room J is in fact less expensive than room I, swap the 2 rooms. Swap their positions. Now the swap function I'm using here is a built-in function provided by the C++ standard template library. Then if I scroll down, you will see that I've defined one operator. In this example, I have defined the stream insertion operator, meaning the cout operator if you prefer to call it that, or the output operator. Right here in this multi-line comment, I have the original block of code. And on line 125, we'll see that every time I want to print a room in my array, I said collection I dot display cout. A very cumbersome line and not very intuitive. Now if I jump down, we'll see that on line 130, it's now just collection I. With operator overloading, I can define how these operators work for types I define. I can define how these operators work for structs I define, for classes I define, for any type I define. Now, let's take a look at how this works. There are two ways of defining the stream insertion operator as something called a friend function, which is discussed in your textbook and in the lecture notes. I won't touch on that here simply because friend functions are not something I often use. There are some cases where they are useful, but in the general case, this is the method you see used for stream insertion operators, the one I'm about to discuss. We see that I have left the display function unmodified. The display function still works in the same way. Still does the same output like we saw in the previous example. What I do is I take my stream insertion operator and I write it in the context of my display function. So if I scroll down here, we'll see the stream insertion operator. Now the stream insertion operator is very interesting. Its return type is a reference to an output stream. The leftmost argument is a reference to the output stream I'm passing. I'm passing in an output stream by reference. And the rightmost argument is my data type passed by constant reference. And at the very end of this function, I have to return the output stream I passed in. This is what allows me to write the really long cout statements that are one after another. Cout a variable x, a variable y, a variable z, and so on. That's what returning the output stream does here. Now, why does it work that way? That's just the mechanic in C++. My return type is a reference to an output stream, and I must return the output stream I pass in. It's just a requirement based on the language, one of those things. But we'll see that my stream insertion operator is little more than a wrapper for my display function. Really, all I've done is said, hey, here's my stream insertion operator. You know what? Just call the display function. Now, the benefit here is, if you look, the stream insertion operator is not defined as a member function, and it cannot be defined as a member function. And I discuss why in CS 330, the course after this. But the stream insertion operator cannot be defined as a pure member function. And you can once again get around with that by defining it as a friend function, but we're not going to do that here. All I'm doing here is saying I'm defining my stream insertion operator. Let's just write it as a wrapper around the display function. This is a technique you see used quite often, calling some display function that is a member function of the class. That is my stream insertion operator in a nutshell. It is really just a function that calls my display function. And the rest of my class remains unmodified. That is the only thing I made. This is the only addition. Now, that is it. That's all that's changed here. A very small change, a very subtle change, but a very useful one nonetheless. Being able to write cout collection I instead of collection I dot display cout. A very, very nice change. But I would very much like to clean up this line here. I'd like to clean that up. I'd like to just say collection J less than collection I and have that work. Now, just like I have defined the stream insertion operator, I'm going to define the less than or comes before operator. And if I'm defining the less than operator, it's a good idea to define my logical equivalence operator, which I'll do here in example 3. So example 3, we see we still have the sort rooms function. We still have the print all room summaries function. Scroll down, my main function remains unchanged. Still the same two function calls. And if I scroll down and I look at my sort rooms function, now we see that I've commented out the original line, collection J dot flooring cost less than collection I dot flooring cost. And I've replaced that with if collection J less than collection I swap. Now this opens up a number of possibilities. Earlier in the lecture notes towards the end of part 2 with arrays, you saw template functions. This now allows me to write a sorting template function. Basically, I can write one version of a sorting function and using templates have it work for anything that has the less than operator and logical equivalence operators defined. Anything that has those two operators defined can use the generic sorting function. And there is a generic sort function in C++, which we'll see in the next example. But beyond this one line, the update room.cpp file, the file that drives everything, has not changed from the previous example. The changes are in my room ADT. So if I scroll down a little bit more, we'll see that I've defined two operators. The logical equivalence operator and the less than operator. Now here I'm defining them as member functions. The logical equivalence and less than operators can be defined as member functions or outside the class. In this case, I've opted for the member function version. So with member functions, the logical equivalence operator has direct access to the current instance, this instance of my room, and I'm passing in a second room by constant reference. And the function itself is constant. Now this means two things. Well, three things actually. The first thing is this has direct access to the current room through the this self pointer, either implicitly or explicitly. I'm passing in a second room right-hand side by constant reference, meaning I have direct access to the original, but I can't change it. And then the function itself is constant, meaning I am changing neither the room I'm passing in for the comparison or the room in which I'm performing the comparison. And the same thing for less than here. Now, you'll note that I have not written these as inline functions. I wrote these within room.cpp. But we see the stream insertion operator is still here. My two comparison operators, logical equivalence and less than, are written here, declared here. And if I scroll down in room.cpp, we'll see that I've defined the two operators here. The logical equivalence operator, return this flooring cost equal right-hand side flooring cost. Now what I'm doing here is comparing the flooring cost of this room to the right-hand side room I passed in. Now in this case, this self pointer is unnecessary. It's superfluous. So in either way, in this point, written this way, I am using the this self pointer implicitly. In this case, I'm using the this self pointer explicitly. I'm explicitly writing it. Now note that I am ignoring errors that arise due to floating point computations, as you've either seen or will see in 361 and later on 417. Floating point is not infinite precision like we have in math. I can only store a limited number of bits, and sometimes we run into rounding errors. So if I have two rooms that should have the same area, depending on a number of factors, even though those areas should match, they don't. They're off by, let's say, 1 millionth. And normally I'd have some sort of rounding logic to deal with that. But in this case, I'm going to assume that I have perfect precision. That is never a case. Then below we'll see that the less than operator is defined in more or less the same way. This flooring cost less than right-hand side flooring cost. Now, these are only two of the logical operators. I can do not equal, less than or equal, greater than or equal, or greater than, any number of operators. And there's a trick to using these two by including the utility library and using namespace standard relops, whereby defining these two functions, I can have the compiler build the rest for me based on these. The compiler will write the rest based on those two compiler tricks, which we'll discuss in a later example. But the point is, these are the only two I need to write, and I can build the rest from these. Once I have these, I can build the rest, either using the compiler trick or by defining the remaining operators in the context of these two. But we'll note that unlike the stream insertion operator here, I have defined the logical equivalence operator as a member function of room, and the less than, more aptly called the comes before operator, as a member function as well. These are both written as member functions. Now, when I return to update room, I need only write this one line. And now that I have those two operators defined, now that I have the less than operator and the comes before operators defined, I can now get rid of this horrible bubble sort code here and use the built-in sorting algorithm. There's a built-in sort function I can use. And that is example 4 here. Okay, so here's the trick. There is a utility header I can include, which I haven't done here, unfortunately. But the trick is I include this using namespace standard roll-ops line along with the utility header, and it will build the rest for me. And we'll see the proper header in the next example, excuse me. At this case, I said, I'm going to keep the sort rooms function for a moment. The main function remains unchanged. But if I look at sort rooms, I've commented out all of this, and I'm using the built-in sort function. Now, the sort function is a little bit tricky. It takes an iterator to the beginning of the data structure and an iterator at the end of your data structure. Something we look at in 330 in more detail. The key takeaway from this is when I overload operators, when I define these operators, I can now use more of the C++ standard template library. And if you've used vectors or lists and you've used one of these functions, that's what allows them to work, by having those two operators, less than and the logical equivalence operator. That's how they work at a basic level. Beginning of my array, end of my array. An iterator to the beginning and an iterator to the end. Once again, iterators is something we discussed in 330 and 361. For now, all you need to do is appreciate that by defining these operators, specifically by defining the less than and logical equivalence operators, I can now make use of these built-in functions. I am now opening the doors for more features of the language. As we scroll down, we'll see that nothing else has changed as well. Now, let's go ahead and run example 4 and take a look. So on the left here, I have what we ran for example 1. And on the right, I'm going to run example 4. Now the first room was 97 cents in our case. Well, it would help if I typed the correct thing first. So 3 rooms, 97 cents for the square footing of this first room. Cost per square foot, excuse me. 3 by 4. Let's do the third room. Let's do the more expensive one first. So the unit cost is $8.97, 14 by 20. And then the third room is $3.97, 4 by 8. And we'll see that those rooms are in fact sorted based on these operators and that built-in sort function. And if you repeat this for example 3, you'll see the same thing. But we'll see that even though I entered them in an unsorted order, the code sorted them based on that call to the sort function and by having those two operators defined. And in example 3, had a similar result with the bubble sort code. And then in example 2, something similar with the bubble sort code and the operators not defined, writing all that code explicitly. But the key takeaway from this is if I define these operators, there are tricks I can use to write less code myself and use code that's provided to me by the language I am using, in this case C++, and exploit the fact that if a sort function is part of the language, it is generally written better than what I would write on the fly. Or it allows me to prototype faster. In either case, by defining these operators, I can now make use of more features of the language, more built-in functions. And we'll see more of this in 330 and 361 in the later courses. Now let's take a look at example 5. Now in example 5, I started looking at this and I said, you know what? I'm using the built-in sorting function. So I'm just going to call that directly in my main function. There's no reason for me to have the sort rooms function if all I'm doing is using the built-in sort function. So if I had been writing this from scratch and define these operators from the beginning, that would have been one less function I have to write. And if I recall correctly, the built-in sort function uses quicksort. A very interesting sorting algorithm, but something you'll see in 361. So that's one function we can remove now. And that's all I've changed in this example. By getting rid of my sort rooms function, simply saying, let's just call the built-in one directly. And that's example 5. And that's really the end of operator overloading. That is the end of operator overloading. That's the end of what we need to know for the assignments in this course and to work on the semester project. Now at this point I have 3 more examples, examples 6, 7, and 8. And these are really topics more suited for CS 330. Something we'll see in CS 330 when we look at more operators we can define and the rules for defining good classes in a deeper context in a more thorough examination. The purpose of this is to build an appreciation for what you can do with these techniques and just the sheer number of operators that exist. I've only discussed 3 in the discussion: less than, logical equivalence, and the stream insertion, the output operator. There are many more I'm not discussing now. What I'm going to discuss here is an interesting technique. Up until this point, we've been using arrays, linked lists, and maybe you've used a vector at some point. I'm going to define my own data structure, my own room collection data structure. Now the goal here is to say, well, I have this collection of rooms, and I want to hide what data structure I'm using. I want to abstract that away. And now once again, if your focus is on the operator overloading assignment, you can stop here. This is really for an appreciation of what we will see in the future. I'm saying, you know what, I have this data structure, room collection, that is multiple rooms. It hides all the how this works for me. At this point, number of rooms is really just for my user prompts. It serves no purpose any longer. And we'll see that I create a temporary new room and I add that to my data structure. And I'll discuss how this function works in a moment. My data structure, my room collection data structure, has a sort function. And my print all room summaries function will note that even though it takes a room collection as an argument, I'm still using the array subscript operator. Now, the array subscript operator, those 2 square brackets, that's an operator you can overload. You can overload that operator for your class, for your ADTs. The important thing is whenever you're overloading an operator, you make sure it makes sense. You can abuse operator overloading. But if you overload an operator, it must make sense. It should be intuitive. You should never overload an operator just because you can. You should be overloading an operator because it needs to be done and because it's the best approach. So this is my room collection data, my room collection ADT. I'm defining a constant max rooms, excuse me. Now you'll note this isn't const int max rooms equals 100. This is a compiler directive, a preprocessor directive. I'm defining a constant max rooms as 100, and I'm using the compiler, the preprocessor, to do so. Now what that does is anywhere I type max rooms, it actually replaces it with 100. Instead of it being a variable in C++, it is a pre-processing directive. The compiler will replace every instance of max rooms with 100. Now if I look at room collection here, it is really just a wrapper for my array of rooms. And here I'm using a dynamic array. I'm saying create an array of 100 rooms, but keep track of the actual size separately. This is very similar, if not almost identical, to the array assignment, where you had the add function, the add word function, and so on. This is almost identical to the arrays assignment, almost identical to that word list ADT. The only difference here is this is an array of room objects, and the assignment, it's an array of word count objects. But same basic thing, where the only difference is really the variable names. My default constructor, my add function, where I take a room I want to add, and you'll see that I've changed my naming convention for variables to use alternating case instead of underscore, something I'll be using for the rest of the semester. A sort function, which sorts all the rooms I have added. A size function that allows me to see how many rooms, how many meaningful rooms I have in my data structure. And the array subscript operator. Now this operator will allow me to assign a new value to that position in my data structure, to retrieve the original, and retrieve a reference to the original, meaning access and modify it directly. And I'm passing in an integer location. Now, in the canonical implementation of this function of an array subscript operator, you generally see size underscore t for the data type. And that's really just an unsigned integer that's always positive. But for our purposes, it's interchangeable with an integer. That's my room collection in a nutshell. Now, I go to roomcollection.cpp, the implementation file. I include the utility header. I include the line using namespace standard relops. And now, because this is going to define all the operators for my room, meaning now, by including these two lines and defining those two operators for a room, I now have a less than operator, a greater than equal, and not equal to operator. All those operators are defined for me by the compiler because of these two lines and the two operators I defined. My room collection constructor, the actual size of my array in the beginning is 0. I have 0 meaningful elements. I can store 100. I've allocated space for 100, but I'm not storing any yet. The room collection add function, I start off with an assertion, and this is unnecessary in most cases, but here I am asserting that the actual size of my array is less than max rooms, meaning I am asserting that I am not trying to add more than 100 rooms to this data structure. And then I say, take the actual size of my array, so if I have no elements, this is going to be 0, and store what I want to add there. Then after I've added that item, increase my count by 1, meaning after I stored that first item, I now have 1 meaningful item. Or by exploiting how the post increment operator works, I could combine these two lines into one. And this is something you will see in most implementations of such an add function. Size, return the actual size. And now this is something I could have written as an inline function but chose not to. Once again, inline functions aren't strictly necessary. They are an optimization trick you can do. And then a sort function for my data structure. Now, normally I wouldn't have a sort function in my data structure. I would define an iterator for this data structure, a begin, an end, and all those specialized functions for my data structure. But once again, those are topics for CS330. Those are topics for a later course. So all I've really done here, as I've said, take the beginning of my rooms array, take the last meaningful elements in my room array and sort them. And here I'm using the ampersand to get the memory address, to essentially get a pointer to room 0 and get a pointer to the end of my array, to the last meaningful element. That's all I'm really doing here. An ugly trick, an ugly hack, an ugly workaround, but one to get the code to work for the sake of this example. And now once again, I will look at this again at the beginning of CS330 next semester with proper begin and end functions and proper iterators. But that's once again a topic for CS330. Now, the array subscript operator. We'll note that inside my room collection, I have an array of rooms. But for my ADT, for the ADT itself, I'm defining the array subscript operator. So really, it's just a wrapper for this one line. Now, is this data structure useful? No. But if I decide to change the internal data structure, for example, if I decide to change this from an array to a linked list, or a vector, or a list, I do not need to change any code that calls this. I can leave update room on unmodified. If I change the inner data structure of this room collection ADT, I need only modify these functions to use the new data structure. Any code that uses this ADT doesn't need to worry about those changes. I am abstracting away the underlying data structure. And then looking at this, I said, you know what? Room collection, if I want to print all the rooms, why not simply say, well, you know what? Why haven't I defined a stream insertion operator for my room collection? Why can't I write cout room collection? So now I want to add an output function. I want to be able to write cout my room. So I add this display function. I add my stream insertion operator here. Once again, you'll see that this is almost identical to the room example, with the only difference being the data type here. And if I look, my display function is essentially me moving this block of code here. And now all I do is go back to my main function, my main file here. Say I have a room collection, all the code's the same. At the very end, I can say rooms is my data structure, cout rooms. It goes to that stream insertion operator I defined, which goes to the display operator I defined, and calls this. All I'm really doing with these operators is moving code around and giving them what's referred to as a canonical name, a name that is accepted as performing this operation, and making it where I can write more fluid code, if you will. Now, once again, examples 6 and 7 are really to motivate what we are going to discuss in later courses, and just to show what we can do with operators, how far the rabbit hole goes, so to speak. Now, the key takeaway from this is operator overloading is powerful. It is a very powerful tool. It is also a very easy to abuse tool. If your focus is purely on the assignments thus far on the semester project, you need only go through example 5 here. And for the final exam, you only need to understand how to write the operators discussed in the lecture notes. You don't need to understand how to overload the array subscript operator, how to overload the typecast operators. But appreciate what examples 6 and 7 demonstrate. Appreciate what you can do and what you will learn.